Hello friends, today we are going to see about entropy production. So here you can see the entropy flow due to exchange of matter and energy. So here you can consider two phases. So there will be a system consists of two phases, phase 1 and 2. This phase 1 and 2 is open with respect to each other, so there will be exchange of matter or energy in between the phases 1 and 2. At the same time, this system, it will be a closed system with respect to the surroundings. With respect to the surrounding, the system will be a closed one, but within this system there is two phases. These both the phases are open to each other, so there will be exchange of matter, energy, etc. So using the Gibbs formula, here you can see, sorry, so here you can see using the Gibbs formula. So you have derived this thermodynamic relation TdS equal to du plus Pdv minus summation of nu c dnc. Here we already know, according to first law of thermodynamics, du is equal to del q minus Pdv. So instead of this du, we are substituting this del q minus Pdv. In same way, dnc, the change in number of moles of components, is equal to nu c into d epsilon. That is the extent of reaction, which you might have studied in the basics when you are discussing about the conservation of mass and energy in the irreversible thermodynamics. So now we are substituting these values in the equation 1. So once we have substituted this, instead of du, if you substitute del q minus Pdv, and instead of dnc, we are substituting minus nu c d epsilon. So if you are doing like this, here you can see the resultant equation will be like this. Here you will be having minus Pdv plus Pdv, which can be cancelled. Now the resultant equation will be, this is the resultant equation. So in this resultant equation, if you bring this t to the opposite side of the equal to sign, so here you can see the equation will changes as follows. Now the t will be moving towards the denominator. So now here you can see, here we are having a new term, new summation of nu c d epsilon, which I have highlighted in red color. So instead of that minus summation of nu c, we can change it into affinity of reaction A. So now you can change it into affinity of reaction A. So now you can see, now you have changed that summation of nu c gamma c into A. So it resulted in the equation 2, in which the A has been substituted, affinity of reaction have been substituted here. So for open system, so since we are discussing about the phase 1 and 2 within the system, which will be acting as an open system, a system inside a system, the two systems inside a system, it is acting as an open system. Here the heat transfer will be replaced by del pi. So instead of heat transfer, here we are, for del q, we are representing it as del pi, which means that there will be flow of energy due to heat transfer and exchange of matter. So there will be both exchange of matter and energy, which leads to the heat transfer. So this del q can be replaced as del pi. So if the del pi is there, we can confirm that it is an open system. So now here you can see the exchange of entropy. So suppose if the system is acting as an open system, if it is exchanging the matter and energy with the surrounding, then the entropy change will be remodified as follows. So when compared to that, in the equation or one, I think the in the previous slide, in the last equation, we may have a similar entropy change equation. Here also we are having same entropy change equation. The only one thing is here we are using the term del pi. Instead of q in that previous slide you might have used del q. Here we are using del pi. So here now you can see the equation 2 can be also rewritten as follows. So in the equation 2 can be rewritten as follows. So ds is equal to, instead of del q, you can write the del pi minus summation of nu c by t d e n c plus a by t d epsilon. So here you can see, so the entropy change is again modified in with respect to the open system. So it is remodified as follows. So here it will be exchanging with the surrounding. This is the entropy change for the system which is exchanging the matter and energy with the surrounding at this juncture. So now you can write the equation 2 in this way. So similar to that of that the entropy equation of the entropy exchange with the surrounding. So here you will be writing, here you can add this term instead of this del q by t, and remaining equations are as such. So for both phases 1 and 3 can be, so the entropy change for the both the phases 1 and 2. So for both the phases 1 and 2, so there are two phases 1 and 2. The two phases inside the system will be exchanging the matter and energy with themselves. So the equation can be written as follows. So the equation is written by taking into consideration of the phase 1 and 2 of the system. So del 1 pi by T1 plus del 2 pi by T2 minus summation of, since there is a exchange of matter, definitely there will be some change in chemical potential between the phase 1 and 2, which is also represented here. Here we have just written it as nu c by 2 t, sorry, nu c by t. But since here in the system we will be having two phases, phase 1 and 2, so we have to individually represent this chemical potential for 1 and 2. So only here we have represented it as nu c1 and nu c2. So denc1 plus again affinity here we in the when we are discussing about the system exchanging with surrounding, we are considering the system as a single system. But when you are discussing about the system alone, it will be having two phases, phase 1 and 2. So individually we have to write the affinity for the both the phases. So only you can see the equation 4 is the expanded version of equation 3, which takes into consideration of two phases, the two phases present in the system. Now here you can see the same equation which I have exhibited in the previous slide. So here you can see A1 and A2 will be the affinity of the reactions taking place in two phases. So affinities of the reactions which taking place, D, E and C means the number of moles transferred from 2 to 1. So here the one D, E and C, the subscript, the superscript 1 represents the exchange of number of moles transferred from phase 2 to phase 1. So the energy flow in the system is, the energy flow in the system is sum of heat flow from surrounding and energy flow from one phase to another phase. So on the whole, so there will be a, energy flow in the system will be, whole system is the heat flow from the surroundings. So how much amount of heat is flowing from surrounding to the system, and energy flow which is taking place within the system between the two phases. So that is given here. So here you can see the first one is exchange of flow of energy from the system 2 to system 1. So the flow of energy means it includes flow, the exchange of heat with the surroundings. So it is represented here del E1 Q by T1, and the exchange of energy from phase 2 to 1. So here what is the assumption is, so I will explain it in a easier way. So here it says that the system has two phases 1 and 2. Here you can see the heat will be exchanged, or heat will be flowing from the surrounding to the system. Since it is a surrounding, it can, the heat flow is from surrounding to the system, it can be represented as QE. At the same time, there will be flow of energy from system 2 to 1 and 1 to 2. It can be represented as del pi. If the flow is from 2 to 1, so it is reaching the 1, the final destination is 1, so it can be represented as del 1 pi. If it is flow, the energy flow is from 2 to 1, we can write it as del 1, 1 pi. If it is flow, the energy flow is from 1 to 2, it can be represented as del 2 pi. So on the whole, when we are discussing about the energy flow in a system 1, it includes the energy heat flow from the system 2 to system 1. At the same time, heat flow from the surrounding to the system. In same way, so when you are discussing about the uh, total matter exchange, total amount of matter exchanged with the phase 2, it includes the amount of heat exchanged by from the surrounding to the system 2. Of course, if the heat is exchanged, or the heat is obtained from the surrounding, definitely it will be moving to the system 1 and 2. Both the system 1 and 2 will experience the heat exchange by the system. So only first you can see del E to Q, which means the heat flow is from the surrounding to the system and then to the phase 2 of the system. And here you can see it is the exchange of energy from the system 2 to 1, sorry, system sorry, 1 to 2, from the system 1 to 2. So here you can see, since the energy, so here consider about the phase 1 and 2. So here you can see the phase 1 and 2. So energy is flowing from the system 2 to 1. So system 1 is gaining energy, so it is represented in the positive sign. At the same time, system 2 is losing the energy. So the losing the energy to whom? It is losing the energy to the system 1. So only it is represented as minus del I1 pi by T2. So this is the reason why we are representing it as a minus in negative sign. At the same time, here you can see there will be a gain of heat, so the temperature will increase. Here loss of heat, so the temperature will decrease. So there will not be same temperature between the phase 1 and phase 2. So only it is represented as del T1 in the fifth equation, and it is represented as T2 in the second equation. So as soon as it loses some energy, it will have the temperature T2, and here it will gain some temperature, it is represented as T1. At the same time, here you can see, so the energy, the amount of energy which lost by the system 2, sorry, the phase 2 will be the gain of the energy by the system 1. So here you can see, here also in the numerator it is given as del 1 I pi. Here also del 1 I pi, that is this much amount, del 1 I pi amount of energy has been gained by the system 1, then that much amount, same amount of energy is lost by the system 2. So substituting the equation 5 and the 6 in the equation 4, we will be getting the, on the whole, the total entropy change which includes the exchange of matter and energy between the two phases of the system and exchange of heat with the surrounding by the system on the whole. So this is the final equation which we will get. So here you can see the term 1 and 2 corresponds to the energy flow due to exchange of heat between system and surrounding. So the first two equations represents the exchange of heat between the system and the surrounding. So how much amount of heat is exchanged between the system and the surrounding, that is that is represented in the first two equations. And the equation 3, 4, 5 and 6 corresponds to entropy production inside the system. So here the equation 3, 4, 5, 6, which will be this, which I have highlighted in the green color, purple color and red color. These four equations corresponds to the entropy production inside the system. So here you can see, so the equation 3 corresponds to the entropy change due to energy exchange between 1 and 2. So if there is a exchange of energy between the phase 1 and 2 within the system, it is represented here. I have highlighted it in the green color. Next, the term 4 corresponds to the entropy change due to exchange of matter. So here, if there is a exchange of matter, obviously if there is exchange of matter, there may be some possibility of chemical reaction which leads to the change in chemical potential. So only here you can see we have represented it in the nu C1 and nu C2. So term 4 corresponds to the entropy change due to the exchange of matter between 1 and 2. And next here you can see the equation 5 and 6, which is highlighted in the red color, which corresponds to the entropy change due to chemical reaction taking place in each phase. So in the suppose there may be some chemical reactions may be taking place individually in the each phases, phase 1 and phase 2. So it can be represented in the equations 5 and 6 which I have highlighted. So the reaction will be individually taking place inside the system 1 and 2. So which is represented, which leads to some entropy change, which is represented as equation in the terms 5 and 6. So now here you can see, now you have to find the rate of entropy of production within the system. So here the rate of entropy production within the system dis by dt. So here this is the total entropy change between the system and surrounding here within the system. So here you are omitting the first two terms, which includes the surrounding also. So the which first two terms, which includes the exchange of heat with the surrounding, so it can be omitted. So the remaining terms are used as such. So here you can see, here in the, when you are writing here d, this is ds, this is ds by dt. So in denominator we are adding dt, that's all. So here also we are adding dt. So here you can see, with dou d epsilon by dt, this is equal to nu. So here you can see, then d epsilon by dt can be replaced with nu. So the d epsilon by dt, so here when you are multiply here also, when you divide by dt, so the d epsilon 1 by dt, it will be equal to nu. The extent of reaction with respect to time is equal to partial rate, which you might have discussed in the basics when you are discussing about the basics of irreversible thermodynamics. So obviously we are replacing these values with nu, the partial rate here. So here you can see the partial rate here, this is replaced by partial rate 1, here this is replaced by partial rate 2. So here you can see this there is an affinity terms. So there is an affinity term which can be generally represented as x. There is a flux or force which is acting, that can be represented as j. So usually the entropy change should be always greater than or equal to 0. It should be positive for a uh, for for any type of process, spontaneous process, it should be always greater than 0. So obviously here you can see it is written as greater than or equal to 0. So this affinity is generally represented as x, and the force or the flux will be generally represented as j. So in generally the equation, the above equation can be written in the general form, that is summation of j into x, that should be always greater than 0. So thank you. Okay, okay.